Hello, welcome. We're very happy to have Aravind Asok here today, who will talk about between algebra and geometry. And how do you like people to ask questions?
Feel free to ask questions throughout. Yeah.
Okay, so go ahead.
All right. Well, thanks very much for the invitation. I'm really happy to give a talk like this. So what I'd like to do today is probably a little different than the kinds of math talks you've heard before. Uh, my goal is to talk about a recurring tension in mathematics, and I'd like to start from a very, very long time ago. One of the key points that I want to make is that mathematical disagreements are not just about getting answers. And I think that's when we learn mathematics, certainly early on, I think our goal is to solve problems and to sort of figure things out. But there are different questions that are sort of behind that, and we should ask, why are we solving those problems in the first place? And so some of the questions I'd like to anticipate today are sort of what objects deserve our study, what methods, when we're studying those objects, should be considered legitimate, what constitutes a satisfactory proof, and what do we mean by understanding? Because in principle, the reason we're solving these problems is to understand something. So I'd like to do this by tracing a sort of episode through history. And my claim is that when different approaches arrive at the same conclusion, or the question maybe is that, do they provide the same kind of understanding? And I'm going to do this involving something which I think is pretty down to earth, which is the Möbius band. So, in order to set the stage for this problem, I'm going to start a lot further back in history. And so, let me start here with a classical problem from Pappus of Alexandria. So, this problem was one of these sort of classical Greek problems. It sort of doesn't matter precisely what the problem is. I just want to set up the language and the kind of discussion. It's not actually going to be central to the point of the talk. But the basic setup is you have four fixed lines and you have some distances you'd like to measure. They're indicated on that diagram right there. And there are some fixed angles. And the point is that you'd like to describe the locus of points P which satisfy some conditions. Now, already I've done something sort of anachronistic, which is I've written this in terms of some sort of equations. If you go and you read the classical Greek texts, these are described very much in words. There aren't equations. This idea of algebra is something that is exactly what I'm going to discuss now. Um, on that diagram, I've indicated, I hope you can see, two small quantities, x and y. All right. So the point I want to make is that Pappus posed this kind of problem, and his solution or his explanation suggested that that locus of points was always a conic section. And for 1,000 years, it was not really understood whether that was really the case. So in 1637, René Descartes wrote this famous little text, La Géométrie. And one of the things that he does in this text is uh, introduce, in some sense, what we might call, well, at least pushing in the direction of our modern algebraic method. So he solved this Pappus problem by giving some names to some quantities in that diagram. So those are the things that I've labeled x and y. And in terms of x and y, he showed that these conditions could be translated into an equation, and those equations were always quadratics and consequently determined a conic section. Um, so so from the point of view of Descartes, and maybe from Pappus to Descartes, the problem was, well, can we solve this problem using some sort of new technique? All right. And I emphasize that Descartes' sort of key move was to introduce these algebraic quantities. And so that's sort of the setup and the use of algebra in this sort of discussion. Um, But Descartes sort of, I want to spend a minute thinking about what Descartes actually did in the context in which he was interested in looking at this problem. So here's some quotes. The first is actually something Descartes wrote in La Géométrie, and the second is from a letter that Descartes wrote to Mersenne. Now maybe you know of him through his famous primes. But Descartes was not working in an intellectual vacuum. One of the reasons that his attention turned to Pappus was that in 1588 there was a new translation of Pappus put out, and so mathematicians were sort of discussing what the proper geometrical methods were to solve these kinds of problems. And so there were two questions which sort of got particular attention in that discussion. And in this part of geometry, there are all these questions about drawing curves. And there are sort of two kinds of curves that were being considered, geometric curves and sort of mechanical curves. And so there are real questions about whether some curves were legitimate and some were illegitimate. So, for example, something like the spiral that sort of circled outwards was not really considered a legitimate curve because it wasn't drawn in some, it was considered a mechanical curve, but not a legitimate geometric curve. Anyway, the point is there's some sort of debate about what sort of objects we should consider, and certainly some things are considered illegitimate and other things are considered legitimate. This might sound very strange when you think about mathematics now. I'm sure when you learn about conic sections, you just imagine, okay, you write down some quadratic, and then the conic sections are the possible solutions to those that kind of an equation that's set up in that term. But in the context of Pappus, there were sort of two classical methods that were also being considered. I highlighted sort of analysis and synthesis. And so analysis is sort of working backwards from a desired conclusion, and synthesis was sort of constructing a forward proof from known facts. And Descartes was really concerned about this method. So Descartes sort of viewed these methods as valuable, but in a fundamental way incomplete. And he also wanted a way to sort of make to distinguish between these sort of illegitimate and legitimate geometric objects. So he wanted to be able to separate the sort of truly geometric things from mechanical things. And so let me just roughly say maybe a little more detail. So geometric curves arise from what we might call algebraic relations among motions, and mechanical curves are more complicated motions that are sort of not captured in this way. It's really difficult to sort of say exactly what they consider legitimate and illegitimate, but it's worth noting that they really did think that a distinction needed to be made. So curves such as circles, conics, and even things like the cissoid were sort of natural in Descartes' framework, but other curves like the Archimedean spiral I mentioned were sort of more problematic. And so Descartes, in sort of proceeding along this way, was not advocating that all curves be admitted into geometry, but he was proposing that you should have sort of algebraic criteria for what should actually count as geometry. But I want to emphasize two more things, which I think are really, really important. And this is the tension that I want to highlight throughout this talk. One of the things that Descartes notices is that the ancients, from his point of view, were really only fixated on some very specific problems. And from his point of view, they were just considering things that they happened to bump into. And he was interested in doing something a lot broader than that. He wanted to have a single method which would apply to a broad class of problems, and that would translate geometry into something more mechanical, namely algebra. And he wanted to eliminate ingenuity in doing this. He wanted a systematic procedure so that anyone could figure things out. So again, there's sort of a democratic, in some sense, impulse. Of course, that didn't really exist in those times, but you want to make knowledge sort of more available to people. And this vision, this sort of mechanization of mathematics, I'd like to claim is a problem that exists even now. So nowadays we call this vision Cartesianism, and it's this idea that mathematical problems can be solved by following general symbolic rules rather than some sort of intuitive or geometric thing. All right, so bullet points. You want a uniform symbolic language, broad applicability, and you want to reduce algebra to geometry. So I'm seeing some chat comments. Was this the start of rationalism? Is Cartesianism also rigor, or is it different? Those are both difficult questions. Maybe I'll put off both of those things because I don't want to get into a discussion about rigor itself. What I would like to, so by some measure, Euclidean arguments are rigorous. I think rigor is something that really only makes sense relative to the kind of language that exists at a particular time. And so from Descartes' point of view, this was a rigorous approach, but I don't know if he would have phrased it in those terms. So I would like to argue that Cartesianism is sort of separate from rigor also because it's a specific approach to it's more about the mechanization or the idea that these things should be done systematically. I don't think we would claim that the kind of more intuitive Euclidean sort of geometric or synthetic proofs were somehow less rigorous. So does that answer the question about Cartesianism versus rigor? Um, and regarding the start of rationalism, I think this is a very difficult question to answer. I would say probably no, but maybe that's something that's better addressed to a historian. So, oops. All right. Um, oh, sorry. So if I don't see the chat, can someone just like speak up and tell me if something is in the chat? I noticed these this time, but I don't always. All right,
Yeah.
so now I'm going to jump forward 100 years or so, um, and I'd like to talk about Newton. So nowadays, you probably think of Newton as one of the fathers of calculus, but one of the things he did was write the Principia Mathematica. And Newton, if you read this first line and you think about some of the other things that he wrote, you might it might suggest that Newton is sort of against algebra. But let me observe that Newton is probably one of the strongest algebraists of his times, but he used algebra to discover various things, identities amongst infinite series. He used it to solve equations and used it to develop the methods that became calculus. But um, Newton was making a sharp distinction between discovery and exposition. So, from Newton's point of view, you could use whatever techniques you want to make discoveries, but the exposition should create some sort of intuition. So, Newton writes geometry was contrived as a means of escaping the tediousness of calculation by the ready drawing of lines. Recent people, by confusing both, have lost the simplicity in which all elegance of geometry consists. So, this is maybe not so explicit. There are other places where Newton explicitly rejects Descartes. He says that Descartes' method is just terrible. We should not be using this algebraic structures. Really, the best proofs are the ones that are entirely geometric. And so he makes this sort of argument that a purely symbolic approach to mathematics along the lines of Cartesianism sort of obscures the thing that we really want, which is geometric intuition. So that's a subtext. He's not saying, but he'll sort of hint at that. Um, and what's important is that Newton sort of is worried that understanding, which he believes comes from these geometric approaches, is being replaced by calculation. And in so doing, we're sacrificing simplicity and elegance. Um, so this is the tension. On the one hand, you have these geometric modes of understanding. And if you've done geometry proofs, sometimes you draw like the right line, and then all of a sudden the diagram sort of you're looking at sort of makes it clear how to understand whatever the question is involved. But frequently you can also introduce algebraic quantities and then do something. So these are two approaches to sort of the same kind of object. Um, so maybe the question that I'd like to focus on is if algebra can detect a geometric phenomenon, has it captured the same understanding? So that's sort of the question that I'd like to focus on through this talk.
Can you repeat that, please?
I said if algebra can detect geometric phenomenon, has it captured the same kind of understanding?
Thank you.
Sure. So I encourage you to actually go and look at Newton's version of the Principia. So, if you looked at any calculus textbooks, nowadays calculus textbooks are these heavy tomes with thousands of pages. I mean, Principia is definitely much thinner. There's a lot of discussion in Principia, but all of the sort of algebraic and infinitesimal reasoning that Newton sort of used to come up with these ideas is hidden, and it's replaced by purely geometric arguments. And it's fun to try to like think about exactly what he does there. Let's see. The original Latin version is like 800 pages, perhaps. But you should think about what else you need to know to read the modern 1,000-page text anyway. Um, um, all right. Other comments. When AI does geometry, does it do it through algebraic means? I will come back to that near the end of the talk. I don't know what it means to say that what AI does. So, all right. Okay. All right. So this is the tension in 2 words or 3 words, geometry or algebra. I think different people have different ideas about which one actually gives understanding. And I'm going to jump forward now another several hundred years. Let's see, what is this one? It chord bashes. All right. Okay, so I'm not going to assume you know complex analysis, but I do want to highlight a few things that illustrate a tension. That, I mean, illustrate this tension that I've described between geometry and algebra sort of continues moving forward. Suppose I start with this geometric series, 1 plus e squared plus dot dot dot. Then you probably all know that for complex values of z, this converges as long as the magnitude of z is less than 1. And of course, within that domain, it can be written in a different way. You can sum this series and describe it as 1 over 1 minus z. And one of the basic observations is that latter formula makes sense far beyond the domain where the original series actually converges. And this is maybe the simplest example of a phenomenon that you might call analytic continuation. You have some function, it's locally defined by a series, but within the domain of convergence, you can express it by some other formula or other way, and the domain in which it actually makes sense can be extended in this way. So analytic continuation is something we study for complex analytic functions all the time. And it came up in Riemann's analysis of differential equations of the second order. But one of the points that I want to make is that it highlights a fundamental distinction. So on the one hand, when we look at series, we think about things like radius of convergence, and that is a very much a local notion. We fix a point and we look in near that point that formula, that series actually makes sense. And nevertheless, there is some, in principle, more global notion there. In this case, the function 1 over 1 minus z makes sense in the entire complex plane, and it's sort of well defined as long as z is not equal to 1. So Riemann, based on this sort of analytic observation, does something quite different. He wants to introduce some geometric idea which is going to unify all of function theory. So in a very, very famous lecture in 1854, which he delivered at Gauss's request, so Riemann was a student of Gauss, and Gauss had studied many, many aspects of geometry that we now talk about in multivariable calculus, for example. And some of that was in the course of developing aspects of electromagnetism. And Riemann was sort of inspired by Gauss to consider notions of geometry that were broader than the things that were considered at the time. So in Gauss, it was common to use what we might now call 2- and 3-dimensional objects, things that we could really picture easily. But Riemann in this lecture, and it really required justification at the time, said we should consider things that are not 2- or 3-dimensional. We should consider things that are higher dimensional. And I want to build some sort of global notion of geometry that sort of allows us to investigate functions. And so the notion that he invented or the notion he suggested, he didn't write down what we might call a definition now, but what he wrote down definitely sort of pushed mathematics in a direction for the next, well, maybe 150 years, was the notion of a manifold. So the idea is that you have a collection of local descriptions, and I'd like to have, in the context of function theory, and I think this is relevant for Riemann, you would really like to think about series expansions of certain kinds of functions. So we have these local descriptions, and yet we want them to sort of be put together and governed by some kind of global entity. So maybe the simplest picture of this is the Riemann sphere. So how can I get the Riemann sphere? Well, this is the complex plane, which I've drawn on the left with the coordinate z, and I've just added a point at infinity. And what I want to point out is that point at infinity isn't just some idealized point, but if we change coordinates and we use the coordinate 1 over z, well, we can also think about the Riemann sphere minus the point 0 as a copy of the complex line in the coordinate 1 over z. And so those two different patches are being sort of glued together, and the transition between the two is I hope, immediate. If you take the Riemann sphere and you remove 0 and infinity, then to go from the description in the z coordinate description to the 1 over z coordinate description, well, what do? Well, you just exchange z for 1 over z. All right, so this notion of manifold is laid out in Riemann's lecture, but it's important to notice that the pictures weren't always as simple as this one. So I'd like to give you a slightly more complicated picture, which I'd like to say a few words about before I change the subject a little bit. All right. Okay, so one of the things that was very popular around Riemann's time was the analysis of these kinds of, well, this one might be called an elliptic integral. So I want to look at the equation y squared equals x times x minus a times x minus 1, where a is some sort of parameter. And just intuitively, I like to think about a as sitting between 0 and 1. And it was very interesting at the time to consider, well, let's fix a point in the complex plane, which is not 0, 1, or a, and let's call it z naught, and then we'll consider integrals of the form integral from z naught to some variable t of dx over the square root of x times x minus a times x minus 1. All right, so there's several different ways we can think about this object. If I look at x squared equals x times x minus a times x minus 1, I can, in essence, so I'm thinking about y and x as complex variables, and I could graph it in the complex plane. This is a little bit hard to picture, but there's several things that I could do. So on the one hand, I can project onto x. And if I think about different x values and I look at the solutions to that equation, then each point that I look at except 0, 1, or a has exactly two pre-images. So I can think about y squared equals that cubic as a geometric object, if I look at its graph, which lives over the complex plane. And if you want, there are sort of two copies of the complex plane that are being glued together along the points 0, 1, and a. All right, so I'm going to do something which is, I hope, kind of intuitive. So I'd like to evaluate these integrals, and one of the things you can observe is that an integral like this has some really beautiful behavior. Um, so if I've made this observation about these two pre-images, if I look at the line segment that connects 0 and a, say in the real line, then that line segment, if I lift it into the graph of y squared equals that cubic, has two pre-images. If you want, you can say that there's a positive pre-image and a negative pre-image. And that gives me a little loop in the graph up top. And I can ask, what happens when I integrate this expression around that loop? Likewise, I can do something similar. Now, here I've written everything in the complex plane, but there is an ideal point at infinity. And so I've also indicated infinity as a point where there's only one pre-image instead of two. And likewise, I can look at the line segment and the real line connecting, going from 1 off to infinity. And it also has two pre-images. And if I include that idealized point at infinity, then those two pre-images will also give me a loop in the graph. And so I can also compute the relevant integral along that cycle, so that little loop. And I would like to observe what happens when a tends to 0. All right, so nowadays we have various ways of picturing an object like this. And so you may have heard that if I graph this thing here, then what I'll get is something that looks like a torus. But in function theoretic times, like when Riemann was studying it, the way we got our hands on those kinds of objects was by looking at things we could actually integrate, by doing calculus. And so this curve, the two cycles that I've just described, can be distinguished by these integrals. If I actually go and compute those integrals, then I get some complex numbers, which are called the periods, and there are two distinct ones. And what happens when I let a tend to 0? Well, I can still do everything that I've said, except I hope you see that loop that I got by lifting the interval between 0 and a just disappears. So nowadays we might say, okay, well, if the picture on the left is described in terms of a torus, and one of the circles on that torus is given by, will be given by that little loop 0a. When we shrink it to a point, we can imagine shrinking one of the sort of defining directions of the torus down to a point. And so something has happened. While the torus, I hope you believe, has a hole, and we've observed that hole by observing that this integral actually has two distinct values on those two distinct loops, that hole seemingly changes in spirit when a tends to 0. All right, so why am I telling you this story? Not because I'm going to tell you a long discussion about complex analysis, but this is just to set the stage. So Riemann wrote a bunch of stuff about function theory in the 1850s, and he used some techniques in order to do this. Namely, he used an existence result for various kinds of analytic functions, which he called the Dirichlet principle. And Riemann's work was very difficult for people who were of his time. And in 1866, two famous German mathematicians, Alfred Clebsch and Paul Gordon, they were trying to really understand what Riemann was doing. And they had a hard time with computing these kinds of integrals and sort of seeing the kinds of answers that one got. Let's see. Are slides meant to be advancing? No, I'm standing on this one. Was Newton's objection pedagogical, or was it more that he thought algebra was aphysical? I'll come back to that a little bit. I think Newton's objection was that he didn't think algebra actually gave you understanding. So it wasn't exactly pedagogical. He just viewed it as a lesser way of knowing. All right. Okay, so the fact that this integral has sort of two values on the left-hand side and basically only one on the right-hand side is encoded in some kind of global fact about the curve that we're talking about. So this actually led to another manifestation of this debate between algebra and geometry. So the kind of singularity that happens here as a goes to zero is something that can be understood in a fairly straightforward way, and that's why I've given you this picture here. It's what's called a nodal singularity. And Clebsch and Gordon looked through Riemann's formulas, which didn't really make any restrictions on singularities, and they just couldn't make sense of them. So what they did was they imposed a hack. They looked at this algebraic equation and they allowed themselves to sort of distinguish singularities into two types. Um, Basically, some that were sort of sufficiently simple, and then they gave a purely algebraic formula for this sort of topological, budding topological idea, basically the number of independent holomorphic integrands. Um, and they thought this was great. But Riemann's student, Friedrich Prim, read Clebsch and Gordon's work, and so Riemann died of tuberculosis in 1866, right before this book came out. And Prim said in a letter, they would never have written something like this in Riemann's lifetime. This sort of totally destroys Riemann's vision. Function theory should be primary. Algebra should come out of function theory, and it should not be the basis for function theory. So he also sort of complained that algebra was sort of doing something bad, and it lacked understanding in the way that function theory did. Now, that would be great, except I mentioned Riemann's tool, sort of schematically, this Dirichlet principle, and well, a few years after Riemann died, it was realized that the Dirichlet principle, or Riemann's application of it, was just wrong. So in the early 1870s, people observed that Riemann's method sort of couldn't work exactly as stated, and and that created some real problems. And in fact, that problem sort of didn't help, or didn't wasn't resolved for a very, very long time. And so at this point, you could say, okay, I want to do function theory and I want to do things a la Riemann, but you also couldn't use Riemann's methods, so you only had algebra in order to work with these kinds of tools. All right, so I will talk about manifolds more generally, just briefly, but there were lots of reasons to study these kinds of things. And so in the 1870s, so like I said, Riemann's techniques were exposed as problematic, and this sort of error, which is actually a fundamental example of what you might call productive error in mathematics. We care about being right, but sometimes being wrong methodologically leads us in very, very interesting directions. This error has been argued as the thing that led to the creation of algebraic geometry as an independent discipline. So take from that what you will. All right, so these Riemannian manifolds, well, even though Riemann didn't give a precise definition, they appeared in all kinds of places. Poincaré found things like this in his analysis of the many-body problem, so they became sort of an object of central focus. And one of the things that Riemann sort of observed, and I think this is the sort of most important thing, is that if we have an equation, then we shouldn't be studying it just by equations or coordinates, but the global structure things like holes and those things that I described on the previous slide as cycles and orientability and various things, those are also objects that we should be paying attention to. So in some sense, Riemann's great contribution was that qualitative geometric features will actually control function theory. And pursuing this analysis has led to a really, really rich modern theory. All right. Okay, so I could go on and give you an entire lecture about complex analysis and the theory of algebraic curves and all kinds of things about the relationship between elliptic integrals, but I'd like to do something completely different, and I would like to focus on a similar geometric object which reveals a slightly different problem from several different points of view. All right, so hopefully you've seen the Möbius band before. This sort of was popularized around 1858. I think it's kind of amusing that we call this the Möbius band. So Möbius, like Riemann, was a student of Gauss, but it's sort of a historical accident that it is called the Möbius band. The person who introduced it was someone named Johann Listing, who also was a student of Gauss and is sometimes referred to as the father of topology. I think in my day-to-day life, I'm a topologist algebraic geometer, and I actually had never heard of Listing before I sort of started looking through the history of the Möbius band. So take from that what you will. But this is an example of what you might call a one-sided surface. So if you take that black line and you start with your finger on one side and you trace it all the way around, then you'll traverse both sides of this little sheet. You stare at this thing, and I hope you see that, well, there's a global twist. How do we build this thing? We can take a strip, and then we glue together two ends by means of the twist. But the thing that I want to focus on is the fact that locally, this thing doesn't look twisted. The twist is something that really is only globally visible. All right. So locally, this object here looks like a small arc times an interval. So if I fix a point on that black circle in the middle, and I look at a little interval of points around there, then I can find basically a copy of a product of two intervals, and locally that's what it looks like. It looks like a flat thing. All right, so I hope you agree that you can look at this and see the twist, and the fact that it's one-sided is actually one way to see the twist. But I would like to pose a different question, which is in the spirit of what I've been talking about, which is, can it be detected by pure algebra? All right, so I'm going to do this in two ways. All right, so we can give a nice parametric equation for the Möbius band. And let me just highlight some features of that. All right, so there's a central circle in there, which I've parameterized by cosine theta and sine theta. So theta is ranging from 0 to 2 pi. And I'd like to first imagine this as a literal band, and the band is going to have width 2 epsilon. All right. And so here is a standard parameterization of the of the Möbius band. So there's a few things I'd like to make. So points I'd like to make, that capital R, if you want, is the radius of the central circle. And one of the things that you can do with this sort of formulaic thing is if I just take x, y, and z and I just project to the x and y directions, or just to cosine theta, sine theta, then I can view this as a map from the Möbius band to that central circle. And if I look at the preimage of any point on that central circle, what is that actually going to look like? Well, it's going to look like a little interval of length 2 epsilon, so from minus epsilon to epsilon. So if I fix theta, then varying t traces out an interval. All right. And here's the key fact. There's a theta over 2 that appears in there. And so as theta ranges from 0 to 2 pi, that expression cosine theta over 2 sine theta over 2 rotates by 180 degrees. It goes from 1, 0 to minus 1, 0. And that is the algebraic, or in this case, analytic encoding of the twist. All right, so now let me make that statement that I made before about locally what it looks like a little bit more precise. So if I restrict in this parametric form theta to a sufficiently small interval, say, something slightly smaller than, so theta minus h to theta plus h, and I look at the preimages of that, then, well, if I look at those formulas, they can be inverted. And so even analytically, and so I get an explicit bijection, in fact, a smooth bijection between that sort of small product and an actual product of intervals. So if you want, you can say that this thing is locally indistinguishable from a rectangle. And if I make that identification and invert all these things, then locally the projection to the circle, which I described above in those coordinate terms, is just the ordinary projection which sends theta t to theta. All right, so here's the amount. This is easier to do if you're actually physical. I have a Möbius band sitting up top. I have a circle sitting down below. And the map that I'm described there is sort of what I'm going to call the projection. That circle I'm going to call the base space. And if I look at a given point on the base, I can look at the preimage, and that preimage is going to be some interval, which I'm going to call the fibers. So the Möbius band is maybe the quintessential example of a modern thing, which is called a fiber bundle. And this comes up in all kinds of geometry now. Maybe initially it was described to give examples of the kinds of manifolds that Riemann was working with. All right. So I'd like to think about this slightly differently. Now, I talked about this as a band, and by that I meant that if I looked at the preimage of any point on this circle, I got basically an interval minus epsilon to epsilon. But you probably know that the interval, or the open interval minus epsilon to epsilon, is actually in bijection with the real line, and there's a formula for it. If I reparameterize and use replacing t by 2 epsilon over pi times some arctan formula, then I can imagine sitting the whole real line within the fibers. So the fibers don't have to go from minus epsilon to epsilon. As S ranges from minus infinity to infinity, I trace out the same thing. So a different way of saying what I just said is, well, the Möbius band can be thought of as attaching a line, not just an interval, to every point on a circle. And then that line is rotating by 180 degrees as I move around. All right, so why am I making that shift? It's a slightly different object, but at least from the standpoint of the kind of function theory we're describing, it's really no different. Pictorially, you can imagine it exactly the same way as the Möbius band that I wrote down before. Okay, so, well, one of the reasons I want to introduce lines is because lines are easy to study, or easier to study, and I can use linear algebra to study lines. So if I fix a point on the circle for some angle theta naught, and I look at the plane that's perpendicular to the circle at that point, and I look at the line, then I can imagine the matrix which is projecting from the full two-dimensional plane onto that line. And well, that line, if I'd like, I can rotate back to a standard line, say either the x-axis or the y-axis. And if I make that rotation, then the matrix that describes the projection is exactly this projection matrix, 1, 0, 0, 0. Right? So I have to do something to write that for every value, and I'll do that momentarily, but let me just leave it at that for the moment. I just want to make one observation about this matrix, which is really silly, and that is that if you square it, you get it back. So this is an idempotent matrix, and I'm going to turn this into a definition. I'm going to say an n by n matrix P is a projection operator if P squared is equal to P. All right, so this is a really simple definition. It might seem completely uninteresting, but it turns out to be something that is actually central in modern mathematics. All right, so let me now say what I said before in a little bit more detail and keeping into account the angle that I've been used. So I said I have this circle, I fix a value theta, and then I want to project onto the line that corresponds to that given value of theta. All right. So if I think about the Möbius line bundle, so again, attaching that line that varies instead of just the interval, then the fiber corresponding to an angle theta is the line which is spanned by this expression here, cosine theta over 2, sine theta over 2. All right. And you can write down the formula for orthogonal projection onto this line. And how do you do that? If you have this matrix, the standard thing is you take the transpose, you multiply it by this, and you get some formula. You can do that. And that's exactly what this Q of theta is. So if you multiply the transpose of that 2 by 1 matrix by itself, you get a 2 by this thing, you get a 2 by 2 matrix. And that has the following formula. Q of theta is cosine squared theta over 2 and blah, 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 blah. All right. So you can now just directly compute that Q of theta is a projection matrix for every value of theta, right? So I encourage you to sit down and do that. But we can also just simplify this a little bit. And this is maybe a fun. So probably know the double angle identities. And if you use those, then you can simplify this expression. And Q of theta becomes 1/2, 1 plus cosine theta, sine theta, sine theta, 1 minus cosine theta. Now, something amusing has happened. I emphasized that this theta over 2 was the thing that gave me the twist from as I moved around from 0 to 2 pi. But that theta over 2 seems to have disappeared in this formula. And well, there's a question of what we should make of that. All right. So the picture that I drew before sort of has hidden this transition into the Möbius line bundle, but let me not worry about that. Okay. So here's a projection matrix, and this is a projection operator in the sense that I just described. So what can I do with it? All right, so I would now like to think a little bit more algebraically. So I'd like to think about the circle totally algebraically. It's given by the equation x squared plus y squared equals 1. Here, x is cosine theta, y is sine theta, if you'd like. And in that parameterization, this matrix Q can be written as 1/2, 1 plus x, y, 1 minus x. All right, so I need to introduce a tiny, tiny bit of algebra. And what I'd like to do is think about functions on the plane, so two functions of two variables, but I'd like to restrict them to thinking about them as functions on the circle. And something changes when I do that, because on the circle, I know that x squared plus y squared is equal to 1. So algebraically, we'll say that we work in a specific ring, namely the ring. In this case, if I'm looking at polynomial functions, I would be looking at this expression r of xy, that's polynomials in two variables. And then I impose the relation x squared plus y squared minus 1. All right. So if I look at that matrix Q and I do algebra thinking about these expressions as expressions in this ring, then a direct calculation using x squared plus y squared equal 1 shows that q squared is equal to q. Chat question. Someone is talking about A1 homotopy theory, island working lane spaces. I would argue, well, since that is exactly what I do, I will say that that is how this tension comes up is actually absolutely fundamental. And I think it's something we like to ignore when we actually do mathematics. And my point in giving this talk is to emphasize that it's just not something we should be ignoring. So, right.
I have a
But
question.
ask me that again later. Question?
Yeah. What do the elements inside the matrix represent?
So that expression 1 plus x, y, 1 minus x, each of those things, I can think about it in many, many different ways. On the one hand, I can think about those expressions as functions themselves on the plane. So you can think about this as a matrix valued in polynomials and two variables. On the other hand, and what's important for my discussion here is I want to think about it as valued in functions that are actually living on the circle as opposed to the entire plane. And that's why I'm going to be working with this condition that x squared plus y squared is equal to 1, right? So for example, if I think about a function of two variables, like x squared plus y squared minus 1 is a function of two variables. But if I restrict that function to the circle, it becomes the function 0. So I would like to allow myself to equate things like that. And so I don't want to get too much into the algebra. This is sort of, but from my point, the point of view here, I would like to just say that we would like to think about polynomials of two variables. But every time we see an expression like x squared plus y squared equals 1, we can replace it. Or anytime we see an expression like x squared plus y squared, we can always just replace it by 1. And so this is going to come up in a few different places.
Thank you.
Sure. So the upshot is that, well, what I claim is that the Möbius band is now encoded by a projection matrix or a projection operator, namely this one that I've written down right here, whose entries are functions on the circle. And just for simplicity, let me call this ring A, just so I don't have to keep writing that complicated expression. So we're going to do a little bit of mechanics in this ring. And in many ways, if you've worked with residue classes or modular arithmetic, the way that we're going to do algebra in this ring A is very similar to the way we work with residue classes. All right. So first of all, I want to say that we can actually see this twist in some global algebraic way. All right. So what does that mean? Well, to see the twist means to say that this thing, at the very least, is not globally the same thing as just a cylinder. I hope you can see that a cylinder is basically the thing that I would get by attaching a line to every point on the circle in a way that's entirely untwisted. So imagine a cylinder of infinite length, if you like. All right. So how am I going to do that? Well, we observe that the fiber, so that line over an angle theta, is spanned by a particular vector, which I'm going to call E of theta. So cosine theta over 2 sine theta over 2. That's the formula I wrote down before. And if I make a continuous choice of non-zero vector in the fibers, then I can always write that as a multiple of E of theta. All right. So in other words, in order to specify that, I need to specify some function lambda of theta. And I'd like to ask that that function is just continuous. Okay. And I would like to assume that that function is always non-zero. Now, of course, if I were a cylinder, then you could imagine how I would do that. I could just, so if there was no global twist, then clearly I can just take any non-zero preimage at every single point, and that's going to give me a continuous choice of non-zero vector. All right, so the existence of a continuous choice of non-zero vector is something that will distinguish the Möbius band from the cylinder. All right, so non-zero is going to be the important thing. All right, so the key fact about the Möbius band is that it's twisted. So as I go from 0 to 2 pi, E of 2 pi is minus E of 0. Right? So that's the thing that makes it twisted. Now, if I have a continuous choice of non-zero vector, well, I parameterize it in terms of theta, so that means that its value at 2 pi must be the same as the value of 0. And combining those two facts, we see that lambda of 2 pi would have to be minus lambda of 0. But lambda is a function of theta, and it changes sign, so it must vanish somewhere by the intermediate value theorem. All right, so that's a contradiction. There can't be a global nowhere vanishing section or a continuous choice of non-zero vector, and that's one way to distinguish the Möbius band from the cylinder. Okay, but I want to stare at this and I mean, this proof is nice, right? Like I think we all, I hope you guys like geometry and the intermediate value theorem, and it sort of makes sense. If you have a continuous function and it crosses, it takes positive and negative values somewhere and on a connected interval, then it's necessarily got to pass through zero. I mean, I've always enjoyed that kind of argument. But I would like to question the argument now. So I wrote down this formula, Q is 1/2 1 plus xy, y 1 minus x, and I said that it encoded the Möbius band. So one of the consequences of our argument is that this matrix Q, well, if you know the way that matrices behave under change of coordinates, so under a linear change of coordinates, a matrix gets conjugated. And so the observation that we've made is that this matrix is not conjugate to the standard projection matrix, which is the diagonal matrix 1, 0 that I wrote down before. But this argument invokes geometry and analysis. There's a continuous nowhere vanishing section, and we should think about what is involved with that. I mean, if you actually want to write down, I mean, the intermediate value theorem I think is quite intuitive, but it does require some effort to actually figure out what it does and how to establish it in some more formal way. But this non-conjugacy statement that I made is entirely algebraic. I'm saying that this matrix here cannot be by means of conjugation turned into this diagonal matrix. I mean, that's a simple algebraic statement. So I think it's pretty natural to ask, does there exist a proof of this fact that uses only algebra? And again, this is sort of a manifestation of this theme, which is, can geometric phenomena be understood purely algebraically? All right, so you can probably guess what I'm going to do next. Let me give you an algebraic proof of this fact, and then we're going to compare. All right, so in order to give you an algebraic proof of this fact, I need one basic observation. So I need to do a little bit of arithmetic in this ring R of xy modulo x squared plus y squared minus 1. All right, so I said we could do this by replacing any instance of x squared plus y squared by 1, but equivalently, that tells me that y squared is 1 minus x squared. All right, so every element of A can be thought of as some expression with coefficients and polynomials in just x by making this substitution. Anytime I see a y squared, I replace it by 1 minus x squared. And so any expression in this ring can always be written in uniquely in the form f plus yg, where f and g are polynomials in a single variable. All right, and now I need one little trick. So in the complex numbers, you know that if you have z is a plus bi, you can form the conjugate a minus bi, and then that allows you to define what's usually called the norm of a complex number, a plus bi times a minus bi. And I'm just going to do something very, very formally similar in algebra. So this expression y satisfies some quadratic equation, and I'm going to define an operation which I'm going to call conjugation on expressions of the form f plus yg by just replacing y by minus y. All right, and so you can now compute what this does. So the norm of a complex number is z bar. Likewise, let me define the norm of an expression here, f plus yg, to be that expression times its conjugate, so f plus yg times f minus yg. And you can just complete what this is, and then simplify using the condition about y squared. And every expression here looks like this. It's f squared minus 1 minus x squared g squared, or equivalently f squared plus x squared minus 1 g squared. And the point that I want to make is that that norm is now a polynomial in one variable x. So the y's have disappeared. And there's another straightforward computation you can do, which is you can observe that this norm is multiplicative. If I take the norm of a times b, then that's the same thing as the norm of a, norm of b. All right. So if you want, one of the things the norm does is it gives us a tool for studying multiplication in this ring using just ordinary polynomials in x. All right, so I hope you agree that this is fairly elementary. I mean, I think the manipulations that are involved here are not particularly complicated. All right, so I need a tiny, tiny bit of algebraic terminology. If you want, we can even forget some of this, but my first claim is that if I look at that projection operator, which I wrote down before, 1/2 1 plus xy, y 1 minus x, then this determines something in terms of that ring A, namely it gives me what's called an ideal. If you want to know where that ideal comes from in terms of Q, Q is a 2 by 2 matrix. I can multiply a column vector with coefficients in A by it and get some expression, and then I can just project onto the first entry of that column. And if you write down what that looks like, it's exactly expressions of the form something times 1 plus x plus something times y, and the collection of all 6 expressions is precisely this idea. All right, so I want to give a slightly different interpretation of the non-triviality of the Möbius band. So if this Möbius band was trivial, then I claim that this ideal would actually be generated by a single element. So here I've written down 2 explicit generators. I've said every element in this ideal is something times 1 plus x times something times y. And my question is, can it just be written as something times h? And I want to just very quickly observe that the norm shows me this is not possible. So if this ideal was generated by a single element, well, what does this ideal consist of? It's some elements. Well, if it was generated by a single element h, then everything would be something times h. So let's compute the norms of elements in I and compare them to the norms of elements in h. So we can compute the norm of 1 plus x, that's 1 plus x squared, and we can compute the norm of y, and that's minus 1 minus x times 1 plus x. And so with a little bit more work, not too much, you can show that the norm of of all the elements of I is actually the ideal generated by 1 plus x. So everything is some multiple of 1 plus x, if it's a norm of something that actually comes from I. All right, but suppose I had that fixed element h, and I wanted to compute its norm. If I had such an element which generated the whole ideal, then the norm would have to be a constant multiple of 1 plus x. But we've computed with the norms of elements in R of x, y, r, so the norm of f plus yg is f squared plus x squared minus 1g squared. And now let's just make a really, really simple observation, which is that this expression f squared plus x squared minus 1g squared is always non-negative if the absolute value of x is bigger than 1. F squared is always bigger than or equal to 0, x squared is minus 1 is always bigger than or equal to 0, and g squared is always bigger than or equal to 0. On the other hand, this expression 1 plus x is not always non-negative if absolute value of x is bigger than 1. So that's a contradiction. All right, so I think that's kind of cool. On the one hand, if we wanted to do this in geometry, then we needed the intermediate value theorem, which I think is intuitive. If we want to do an algebra, we needed this trick, which was this norm. It's not completely clear where that came from. You'd have to come up with that idea. But I hope you agree that the argument is actually simpler in some ways. It's sort of formulaically much, much simpler. Both arguments sort of relied on some kind of sign computation via the intermediate value theorem in the geometric case and just this observation about polynomials in one variable in the algebraic case. But both sort of give me some idea of how to interpret this proof. So let me just summarize this. The Möbius band began life as sort of this purely geometric object. The twist is something which is sort of less rigid than the geometry, and so it fits nicely into the world of topology. This twist can be encoded purely algebraically by means of this projection operator, and that encoding leaves a trace in what you might call the arithmetic of r of xy modulo x squared plus y squared minus 1. So Möbius band in this context shows that algebra can detect a twist, but I would like you to think about what has been gained and been lost by each of these different arguments. So on the one hand, the algebraic argument reveals some new interesting algebraic features, introduces this notion of a norm, and that, if you want, is potentially a tool that tells us things about arithmetic around rings like this. But the geometric object was sort of more, I think, intuitive, but maybe that's just a function of the fact that we learn about continuous functions before we learn about these kinds of algebraic things. So again, which of these reveals understanding? Do we understand the twist in the Möbius band better or differently because of the existence of this sort of arithmetic fact? And I think this is just another reflection of the same question that Newton, or the same dispute that Newton and Descartes were having. So let me quit there.
Yeah, thanks for a great talk.
Thank
So,
you.
are there any questions now?
Well, I've heard that this has like how do you, I suppose, how did you do you just get that idea from the projection from the Mobius strip onto the circle? Is
So like I said, once you've written down this operator Q,
yeah.
you can think about, so it's a 2 by 2 matrix, so it acts on
Hmm.
column vectors with elements in A. And if I just literally multiply a column vector with by left multiply a column vector with coefficients in A by Q, then I get expressions of the form something. So if my column vector has elements A, B, then just computing, I get A times 1 plus X times or plus B times Y. And that is precisely the collection of all such things as I arrange through A and B is exactly
Yeah,
the,
that's the idea, right?
so
And,
I just project after onto the first column after I do.
mm. And I guess second question is, how would that, I mean, does this then, is this a point? Is this a maximal ideal or like, no, I suppose.
So if you want fancy terminology, R of xy modulo x squared plus y squared minus 1 is a Dedekind domain. And so every non-zero prime ideal is maximal.
Okay, so it is. So is this a prime ideal then?
It's not,
Like,
I mean, it's a non-zero ideal. So that is indeed the question.
all right.
Fun exercise.
All right, I'll think about it with you. for a bit. Anyhow, yeah, thanks.
Sure. So maybe one of the points that I want to make is that, in mathematics, it's not always about solving a problem, right? Here, the problem, and I think we've for a long time believed that the Möbius band was non-trivial. And it's a question of sort of when we build a conceptualization for a particular notion, sort of how does that reflect understanding? And the kinds of problems we can even phrase, I think, they're mediated by the language which we even have to phrase them. And I think that's a really important observation. No one's going back to the motivic homotopy theory stuff.
Yeah. Are there any other questions? Okay, well, if not, then thanks again. And that concludes this part of the class. So let me stop the recording here.